In this video, we will be discussing about optical isomerism. Optical isomerism arises due to the behavior of a molecule towards plane polarized light. So, optical isomers are isomers which differ in their behavior towards plane polarized light, and this phenomena is termed as optical activity or optical isomerism. So, those molecules which rotate the plane polarized light towards right are termed as dextrorotatory, and usually they are denoted by a plus sign or a small letter D. And those compounds which rotate the plane polarized light to left are termed as levorotatory, and they are usually denoted using a minus sign or a small letter L. So when you are discussing about optical activity or optical isomers, there are two important things. The first thing is the specialty of light that you are using. So the light we are using will be plane polarized light. And the second thing is the stereochemistry of the molecule, which is the reason for for this kind of optical activity. So the ordinary light that we see will be having large number of wavelengths, and all these wavelengths will be, or all these waves will be vibrating in a plane that is perpendicular to the plane of propagation of light. So this ordinary light can be converted to a monochromatic light by passing through a suitable filter. A monochromatic light is a light which is having a single wavelength. So usually this kind of light can be produced using various sources such as sodium vapor lamp, etc. And they will be having a single wavelength, but the waves will be vibrating in all possible planes. And when this monochromatic light is passed through a polarizer, an example is nickel prism, it will be converted to plane polarized light. Here you can see an animation using which we can convert a unpolarized light to a polarized light by passing through a polarizer. So here you can see in this figure you have a monochromatic radiation, light that is monochromatic nature, and it is passed through a polarizer, and this polarizer converts this monochromatic light to a plane polarized light. And this plane polarized light is allowed to pass through a sample tube which contains optically active compound. Here you have a solution of optically active compound, and this plane polarized light, upon passing through this sample solution, will be undergoing a rotation, and ultimately you can see the plane of vibration have been shifted an alpha degree, and this is termed as alpha, and this is the observed rotation when the light passes through the sample. And another nickel prism can be used in this region as an analyzer to know how much degree this particular rotation occurs. The instrument that we use for measuring the optical rotation is polarimeter. So the angle of rotation depends on two important factors, that is the concentration of solution and the length of polarimeter tube at a fixed temperature as well as a fixed wavelength. When you are using a fixed wavelength and a fixed temperature, these two factors will be affecting how much the plane of the light is rotated. So here you can see the figure of a instrument, and in this instrument, here in this region you will be having the monochromatic source, and light rays will be coming from here, and it will be converted to a plane polarized light, and here you will be keeping the sample, and after passing through the sample the light will reach here, where you will be having another nickel prism or something for analyzing the rotation, and you can actually see the light through here. And this is the basic instrument that is used for measuring the optical rotation. An important thing when you are discussing optical activity is the specific rotation. It is actually an intrinsic property, and it is used to compare the optical rotation of various substances. So this particular specific rotation will be different when the wavelength is changed. So you have to compare the wavelength and the rotation of various compounds by fixing a particular wavelength. Also, the temperature has to be fixed. So specific rotation of an optically active substance at a given temperature for a given wavelength may be defined as the rotation in degrees produced by a path length of 1 decimeter length in a substance of unit density. So here the concentration should be unity, that is 1 gram per 100 ml, and the path length should be 1 decimeter. So the specific rotation can be shown like this: alpha T lambda is equal to lambda divided by C into T, and T and lambda are the temperature and wavelength that is used for studying the particular sample, and C is the concentration in gram per 100 ml, and L is the path length in decimeter. Now coming to the next thing, that is we have already said that the light we are using should be plane polarized light, and the second thing is about the molecule. So does all the molecule that we see in chemistry show optical activity? No, of course not. Only some molecule will be showing optical activity and other will not be showing optical activity. The main reason for optical activity has been studied that those compounds which are chiral will be optically active. So what is chirality? Chirality is a property of non-superimposability of a structure on its mirror image. So if you have two molecules which are not superimposable to each other, or a molecule which is having a non-superimposable mirror image, is said to be chiral, and this molecule will be optically active. So the basic condition for optical activity of a molecule is chirality. Chirality is the property of non-superimposability of a structure on its mirror image. So all chiral molecules will be optically active. So here you can see some examples for chiral and achiral objects. So here you can, this is the simplest example, your left hand and your right hand, and they are actually mirror images, and they are not superimposable, and you can term them as chiral objects. But an Erlenmeyer flask, the mirror image is exactly the same as the object, so they will be they can be superimposed, and hence they will be achiral objects. And in the alphabets also you can see various chiral and as well as achiral alphabets. P is a chiral alphabet whereas A is an achiral alphabet, and you can find some more examples, but here we are just confining to these simple examples to just get an idea of chirality and achirality. Coming to organic compounds or molecules, the simplest molecule will be a carbon that is in a tetrahedral sp3 hybridized in tetrahedral state, which is attached to 4 groups. If the 4 groups are different, this carbon will be having a non-superimposable mirror image, and hence this will be optically active. This will be chiral. So if you have a molecule which is having a carbon which is attached to 4 different groups, then obviously you can say that molecule is chiral and therefore it is optically active. So by simply looking at a molecule, you can say whether that is chiral or achiral if the molecule has a carbon that is attached to 4 different groups. This is the simplest kind of explanation that can be in the case of structure that can be given for chirality. However, it has been observed that various compounds which does not have a chiral carbon can show optical activity. The chiral carbon is a carbon that is attached to 4 different groups, and in these species, that is cyclooctadecene, alkylidene compounds, allenes, and biphenyl, substituted biphenyls. This doesn't have a chiral carbon, but these species can also show optical activity in addition to the tetrahedral or chiral carbon, or the molecules that has a chiral carbon. So the basic condition for a compound to show optical activity is chirality. All these compounds will be having non-superimposable mirror image. So having a carbon that is attached to 4 different groups is not the mandatory condition for optical activity, but for a molecule to show optical activity, it should have a non-superimposable mirror image. So all these compounds will be having a non-superimposable mirror image, and hence they will be chiral and they will be showing optical activity. So you can actually see like this, all these are optically active compounds, and the majority of the group will be compounds having a chiral carbon or a asymmetric carbon, that is a carbon attached to 4 different groups, and there will be a small group of compounds which does not have a chiral carbon, but they will be having chirality, they will be showing chirality. That is due to the structure of that molecules. So when you are looking into a molecule, you can actually, by using symmetry, you can predict whether that molecule is optically active or not, or whether that molecule is chiral or not. So the main symmetry elements are plane of symmetry, center of symmetry, axis of symmetry, and alternating axis of symmetry. And we all know plane of symmetry is an imaginary plane that bisects a molecule into halves that are mirror images of each other. And center of symmetry is an imaginary point in the molecule, that is, if a line is drawn from any group of the molecule to this point and then extended to an equal distance beyond the point meets an identical group, this is the center of symmetry. An axis of symmetry is an imaginary axis around which, by rotating through a minimum angle of rotation, the original compound will be obtained. An alternating axis of symmetry is actually a combination of 2 symmetry operations, that is it will be a reflection as well as a rotation. So it is a line passing through the molecule around which, if rotated through the angle x followed by reflection in a mirror placed at right angle to the axis, produces the same phase of the molecule. So here you have 2 symmetry operation, one is reflection and another one is rotation. So using these symmetry elements, you can predict whether the molecule is chiral or not. So as we mentioned earlier, plane of symmetry is an imaginary plane. In the case of BF3, boron trifluoride, you can see there will be a plane like this, on which the molecule will be lying, or you can have a plane like 3 planes like this. And center of symmetry, in the case of PTCl4, you can have center of symmetry. The center of symmetry, the point will be on platinum, and if you draw a line from this chlorine to platinum and then extend the same distance to the opposite side, you will be reaching a same group or same chlorine atom. So this is having a center of symmetry. And axis of symmetry, and in the case of BF3 itself, we can see the axis of symmetry. If BF3 is rotated about 120 degree like this, you will be getting another same structure, and you can again rotate it 120 degree to get another same structure. So this is having a axis of symmetry, and another axis of symmetry is also there. We are not going in depth into this particular symmetry elements, but we are just briefly discussing. And alternating axis symmetry, in the case of this molecule, you can see if you rotate this molecule by 180 degree through this axis and then give take a reflection, you will be getting this similar structure. So how can we actually combine or correlate this symmetry as well as optical activity? So the basic thing is, all asymmetric molecules will be optically active. So asymmetric molecule means they do not have any element of symmetry. So carbon that is attached to 4 different groups is obviously an asymmetric molecule, and they will be showing optical activity, and asymmetric molecules will be showing optical activity. And another important group that will be showing optical activity is dissymmetric molecule. So any molecule that does not have a plane of symmetry, center of symmetry, and alternating axis of symmetry is termed as dissymmetric molecule. So if you consider a molecule and look into the symmetry elements of the molecule, and if you cannot find a plane of symmetry, a center of symmetry, and an alternating axis of symmetry, then you can obviously think that it is optically active molecule. So all dissymmetric molecules will be optically active, and asymmetric molecules will be obviously they will not be having any plane of symmetry, center of symmetry, and alternating axis of symmetry, so they will also be optically active. So in the case of symmetry, you can say dissymmetry is the basic condition for optical activity. So if you look into a molecule and analyze whether that molecule is dissymmetric or not, you can say whether that molecule is optically active or not. So using symmetry also you can say whether the molecule is optically active. So in brief, we have seen what is optical activity, how you can analyze a molecule whether it is optically active or not, that is by using a plane polarized light. What happens to the plane polarized light? The plane polarized light would be rotated to right or left. So what is the reason for optical activity? That is due to the stereochemistry of the molecule, due to the difference in orientation of the groups of the molecule. And which all molecules will show optical activity? Does all molecules show optical activity? No, only chiral molecule will be showing optical activity. And what is chirality? Chirality is actually non-superimposability of a molecule and its mirror image. And coming to symmetry, all dissymmetric molecules will be showing optical activity, and dissymmetry is the basic condition for optical activity. That's all. Thank you.